Imagine you've got two anvils. To the naked eye, they look completely identical. They weigh the same, they have the same shape. But if you take a sledgehammer to them, one shatters like it's made of glass, while the other it just dents. They're both cast iron. So what gives them such radically different personalities? Let's dive in.
So on one side, you have your traditional gray cast iron. It's great under compression, but if you try to pull it or bend it, it's incredibly brittle. On the other side, you've got ductile iron. This stuff can bend, it can deform, and it can soak up a ton of energy before it even thinks about failing. It is tough. And yet, if you were to analyze them, their chemical makeup is almost exactly the same.
So what is the hidden difference? To figure that out, we can't just stay on the surface. We have to go microscopic. We need to understand what's happening deep down inside the metal itself as it's being made.
Okay, so our investigation is going to start by looking at this inner flaw, the thing that plagues most common cast iron. And really, it's a story all about carbon, and more importantly, its shape.
In your standard gray cast iron, there's extra carbon in the molten metal that forms into graphite. But here's the key. As the iron cools and turns solid, that graphite precipitates out as these sharp, flat flakes. And as you're about to see, the shape of those flakes, well, it's everything.
These little graphite flakes are basically microscopic stress concentrators. The best way to think about them is like having millions of tiny razor-sharp blades embedded all throughout the metal. So when you apply any kind of force, a crack can start super easily right at the tip of one of these flakes and then just zip right through the material, causing it to shatter with almost no warning. That's the source of its brittleness. So, if the flakes are the bad guy in this story, how do you fix it? Well, the answer isn't to just get rid of the graphite. The real solution is to fundamentally re-engineer its shape. And this is the big breakthrough. Instead of these sharp, crack-starting flakes, what if you could convince the carbon to form perfect little spheres, or nodules? You see, a sphere is pretty much the perfect shape to get rid of stress points. It lets the metal structure around it flow and deform, creating a material that isn't brittle, but is, ductile. Now, to pull off this transformation, you need a really precise three-step process. First, you have to desulfurize the iron, basically get rid of sulfur, because that element loves to make flakes. Second, you nodularize it by adding a tiny, very precise amount of magnesium. This is the magic ingredient, the thing that forces the graphite to grow into a sphere. And finally, you inoculate the molten iron to create what are called nucleation sites. Just think of them as seeds for these tiny graphite spheres to start forming on.
Now, this sounds pretty straightforward, right? But that second step, adding the magnesium, that's where art, science, and just sheer chaos all collide.
And yeah, this picture says it all. Adding magnesium to a ladle of molten iron isn't a gentle stir. It is a violent, pyrotechnic event. It's literally a carefully controlled explosion. And to understand why it's so critical to get this right, we need to look at the numbers. So here's the heart of the problem. Magnesium boils and turns into a gas at just a little over 1,000 degrees Celsius. But the molten iron you're adding it to, that's over 1,400 degrees. So the moment the magnesium hits the iron, it instantly vaporizes. And that's what creates that incredibly intense, fiery reaction.
This extreme volatility, that's the central challenge of making ductile iron. I mean, how do you make sure that this violent, super-fast reaction distributes that tiny amount of magnesium perfectly to create millions of flawless graphite spheres in every single casting? For a really long time, it was more of a dark art than a science.
So how do you actually tame this chaotic process? Well, the modern solution is to find a way to see what's happening inside the molten iron in real time, to, in a way, listen to the metal as it solidifies. This quote just nails the shift in thinking. Instead of just following a chemical recipe and kind of hoping for the best, the modern way is to directly measure the physical process of solidification. You're not guessing based on the ingredients, you're actually watching the cake bake. And this is how they do it. This graph is a thermal analysis cooling curve. Honestly, the best way to think of it is like an EKG for molten iron. A sensor measures the temperature of a sample as it cools and solidifies, and the specific shape of this curve, the dips and the bumps, is a direct signature of how that graphite is forming. The key signal they are listening for is a phenomenon called recalescence. As the liquid iron turns solid, it lets out this burst of energy. It's called latent heat, which actually causes the temperature to spike back up for a second. The size and the shape of that bump, which you can see here at point B, tells the foundry everything it needs to know. A small, sharp bump means you've got perfect spherical graphite. A larger, broader bump means something went wrong. And this ability to listen to the metal
is what transforms ductile iron production from this unstable art into a highly reliable, disciplined science.
This microstructured chessboard is a fantastic way to visualize just how sensitive this process really is. The horizontal axis is how much magnesium treatment you have, and the vertical axis is how much inoculation, those seeds we talked about, you have. You can see how even tiny little changes create totally different structures, all the way from useless flakes down on the bottom left to the perfect spheres you need for high-quality ductile iron in that tiny little box in the top right. The goal is to hit that target every single time.
This is the single most important takeaway from all of this. You would think, right, that if you use the exact same chemical recipe every single time, you'd get a consistent product. But you don't. And why is that? Because other things like the temperature or trace elements in the scrap metal you're using are always changing. Process control beats chemical consistency.
So what this all boils down to is this. By using thermal analysis to listen to each individual ladle of iron, a foundry can see exactly what that specific batch needs. Maybe it needs a tiny bit more magnesium, or just a touch more inoculant. They can make these adjustments on the fly, dynamically, to make sure every single casting hits that narrow target for quality and reliability.
So the next time you see some heavy-duty iron part, like a pipe or a piece of an engine, remember the violent, controlled science that's hidden deep inside it. It really makes you wonder, if this much engineering is needed to perfect something as common as iron, what other everyday materials are hiding these incredible stories of science and innovation just beneath the surface?